Thank you guys for coming. Let's give a warm welcome to Shmuel Friedland from the University of Illinois in Chicago. He's going to be talking about the analysis of big multidimensional data.
Okay, thank you, Dan. Thank you very much. It's my pleasure to be here. Just I volunteered myself to give a talk. And since I don't know what is the audience, and I was told that on Google one should be relaxed, so I didn't prepare that much. What I sort of collected is the things that I gave lectures in the last 2 years on this subject, and maybe it's interesting for you guys or not. So please feel free to interrupt me and and to ask questions. Okay, so what I'm trying to do, let's see if there is a pointer here. So I'm trying to to tell you a little bit about what I did in this area of analysis of some data. Now, usually one is interested at least in two-dimensional data, like a picture, or we'll say I have more like web pages. So the question is how to okay, let's see. So maybe it's more convenient that I will stand here. So the question is, number one is that usually a big data which is multidimensional, it comes there is a lot of reductive information, like a picture. There is a lot of repetition, and what one wants to do if one wants to storage the data is somehow to have a mathematical tool to reduce the data in such a way that you have most of the information to store it. The second thing is denoising data. So sometimes you see that something doesn't fit, so how would you filter the data? And in certain problems, I'm not sure if this is related to problems which you are doing, is there is sometimes a missing data. So you look, let's say, in a photo, and you see something which are blank spots, or maybe you see corrupted spots. So is there any way to correct it mathematically? Okay, so essentially for two-dimensional data as a photo and some other stuff, I think, well, there are always many ways to do that. But one very useful tool that is singular value decomposition. And it was applied to many different problems, and usually it works very good. Now, so this is I will show you the strengths and what kind of problems one can do if you do this two-dimensional thing. So for example, how one can do a fast low-rank approximation. And so this would be in order to reduce the storage. Then if you, suppose you have let's say, if you go to DNA, which has also a lot of data, and we are talking about microarrays, for example. So you want to compare like two things. You want to compare like two certain photos, but it's not exactly photos. And you want to compare, let's say, a photo of elephant to a photo of human and see what is common. Well, and so that is, there is also a way to do it using SVD. Now, and that's I will discuss in detail. Now, much more interesting, or let's say much more challenging, are data which is multidimensional, like three-dimensional picture, or you have voice. So those are, in mathematics, are called tensors. And now the theory singular value decomposition breaks down. Now, it is very important, for example, in an area of face recognition, because you want, to see a person and to recognize it on a photo for many various reasons. I don't know if Google is already in this area, but maybe not. But it is very important. And so for that, usually what one does is takes, let's say, photo of the same person in several profiles, and so it has a tensor and how to identify that. So this, I mean, this is sort of mathematically is very wide open. Okay, so now, so this was sort of what I am trying to do, and if you really are interested in more details, and you can find some of that on my website. So most of the things that I have is lectures that I gave. I didn't prepare any special thing for Google. So now let's talk about, let's see sort of the first, okay, let's see if I can do it here. View, actual, so that's, I mean, let's see if fit page, let's see, okay. So see, so this talk I gave about, well, a year ago. So here sort of we can see the problem is with the colors. Okay, here I see this. I don't know, maybe from the distance you look, you can see it. But anyway, so the problem is as follows. So here, suppose you have a picture. So what is a picture? Is essentially, let's say it is, if you have a standard picture, it would be, say, maybe 5 by 12 by 5 by 12 matrix, and each point you have a pixel. So okay, maybe it has a color and a density. But here in this case, let's assume that it has only one variable. So because we are talking about matrix, if this each let's say point here had also more information like what kind of color, etc., this would be already a tensor. Or so sometimes you have the DNA microarray, which would be like 60,000, the number of genes and the number of experiment what you do. Now here is maybe what Google is more interested is, suppose you look at the web pages. So then Aij, this entry would be the number of times web page J was accessed from web I, okay? So that would be, well, a very big matrix, of course. So now, so in this, so how about condense the data and store it effectively. So for that, so just before I start to do mathematics, because I say I'm not sure if you're interested, so let's look at this example. So what you have here, okay, so I better look what's there because I cannot read it. So on this side, you have the original picture. Now this picture comes from, I think, MATLAB Toolbox. Now, and this is a compression here. How big is the compression? Okay, so this would be the compression. Maybe would be, this is, let's say, 80, maybe 30, maybe 33%. So this is actually maybe the compression would be close to. So 512, maybe, okay, maybe 1/8, okay? So let's say you just have 30% of information here. Now, can you tell the difference? Well, I mean, I cannot tell. Maybe if you look little bit more precisely, see that here is maybe is slightly worse. But anyway, so this is example number 1. And then I'll explain what we do here. Let's take example number 2. So this is the same example. So this is a smaller picture. The pixel is 256 by 256. And so here I think you can see that this is slightly less clear than this one. So okay, so here you can see maybe the difference. So okay, so what are the tools here? Now, so again, I mean, I don't want to, I mean, I'm not sure about my audience. I don't know if I should go to all these formulas, but basically, so I'll just say in words, the formulas are not that important unless one needs to use it. So what is SVD, is singular value decomposition. So if somebody remembers about symmetric matrices, well, it would be spectral decomposition. But this, usually a matrix, this matrix, it doesn't have to be a square matrix. You don't have, look at even the screen here. It's not square. So the matrix is rectangular. So what you want to do, you want to find two orthogonal matrices such that A U times sigma V is going to be your matrix. Now, why orthogonal? Because orthogonal they distort as less as possible. Or in other words, orthogonal means that you have orthogonal rotation of your coordinates. And sigma, this is a diagonal matrix. So the information just sits on the diagonal. Okay. So now, when yes.
So from coming at this from an engineering perspective, is SVD the same thing as finding the eigenvalues of the matrix?
Well, it is very close, but not precise. Suppose if it was a matrix was symmetric, it's then symmetric. Yes, it would be the same. But if metric is not symmetric, we have to symmetrize that. So essentially what we take A times A transposed, and you get a symmetric matrix. So this gives you sort of the or eigenvectors of A transpose, which is called, I think, left or right eigenvectors, not important right now. And then you have to use that to obtain the other part. So it's very close what you say, but not exactly. So for symmetric matrices, the answer yes. For non-symmetric matrices, you have to do this A transpose A.
And with eigenvalues and eigenvectors, then you have the property that the eigenvector will be preserved, it will just be changed in magnitude. Will that same sort of a thing hold here?
Okay, so in other words, you're asking me what happens if you sort of multiply matrix by orthogonal matrix from left and from right? Is that what you mean?
Yeah, I'm wondering if if SVD gives you some of the same properties, just so I can kind of understand it from a physical sense, whether you will have vectors that when they're taken against this matrix will be preserved, but they'll just be changed in magnitude. Is that the same meaning that you're getting with SVD?
Okay, so let's let me see if I still okay. So I mean, if suppose we take any orthonormal basis, that's what you mean. There's anything to do with eigenvectors. So you can take your vector and expand it in, let's say, Fourier series. You can expand your vector in another, not exactly Fourier series, but the coefficient would be different. But you will, in other words, if you can expand it, we have the same vectors. That was your question, something like? Oh yes, that is sort of yes, but that has anything to do with the matrix. So you see, unless it's unless, see, if you have here sort of this matrix, orthogonal matrix means you change a basis. You change a basis. So think about it, Earth, and now you just rotate it in several. So that's a change base. So the same vector, that's what I tell to my students. If you stand here or stand in New York, it won't be the same, but it would different representation. So, okay, let's try to continue. So but on the other hand, it's good that you're asking the question. So now we're going back to a classical result, which is probably 100 years old and was discovered by Schmidt. So now, what does it mean that your data has a lot of, let's say, a lot of redundancy? It means that the rank of a matrix is much smaller than the matrix. So, for example, let's say, so how can I sort of convince you or give you a feeling? You say, so I'm looking, if I look at rank of a matrix, I can look, let's say, in each row. So let's say here, let's say 5, 12 rows, so you can each row. So you look in this row and you look in row by row, is almost look the same. So it's linearly dependent. Of course, there suddenly you come to something. So to say that data is reductive in terms of matrices, it means that you have many dependent rows. And so therefore, So the idea mathematically is that you have many singular values which are close to 0. So again, so if you sort of feel sort of more comfortable with thinking that about eigenvalues, eigenvectors, so think of this, you have a symmetric something, you have a picture that has sort of, so it has a symmetricity. In reality, you won't have it. But so then it means that you have many eigenvalues close to 0. So you say, okay, so if they're close to 0, then let's just discard them. So therefore, if I want to do, this is one way, there are many ways, but we are talking about this way. If you want to do data reduction, you say, okay, I want to approximate my given matrix by a matrix of much lower rank. And so it is standard thing in approximation theory or in reality. I want to, let's say, I want to take some differential equation with many frequencies and approximate by only finite frequencies. So what I would do? Well, I say, okay, we would like to approximate in our finite parameter space as close as possible. That is standard idea in engineering and mathematics. So essentially, okay, I mean, I'm not sure how much technical I should go, but just, so what you do is, okay, I'm looking at all matrices of rank less equals than k, so it's called RMN. This is the dimension of a matrix thing 512 by 512. And so in this picture that I had before, okay, so let's go to this picture. So this was 512, 512. So then the rank of the maximum rank of the matrix can be only 512. But there are many redundancies. Okay, let's try to approximate here 80 rank. So instead of 512 maximum rank, 80 rank. So this is, let's say, roughly 6 times. Okay. And so you see, so when you do that, if you do it right, you lose very little information. So the question is, okay, how to do it right? You know, how to take this matrix B of rank 80 at most, it would be as close as possible. Now, so here, so when we say to data close as possible, what do we mean? So the simplest thing is to think is, okay, so how do I measure distance between 2 points? It has 3 coordinates, so I take sum of the squares of the different coordinates, right? So here, so this one you can think about it, as a, as a sum of the squares of all the entry. And square root because the distance. In mathematics, we call it the Frobenius norm, just in honor of some German mathematician, Frobenius. All these guys lived in the beginning of 20th century. So, but you can also use other norms. But right now, we don't want to be technical. So we want to approximate our matrix A, our data, with lower rank. And how to do it right, and what is the right rank. So that's where the SVD decompositions come into picture. It says that essentially, if you do the SVD decomposition of A, and then you will take this, if you think about it, let's say, in terms of symmetric matrix, you take only the I, let's say, like in music, instead of take all frequencies, I'm going to take the first 50 with no top frequencies and corresponding modes. This is it. So this is exactly the same idea. But now how to do it? Well, it's mathematics. Okay. So, and the question is, okay, so what is essentially, what would be, how many modes I should take? First 100 or first 50? Well, it depends. You see, you look at that, let's say, at your picture and see, well, actually, I have only 50 big modes. So they'll take the first 50. So how do we know that? Well, it's sort of, it's a more, now becomes engineering problem and art. Now, so when you had this picture, and you look at this picture of, what is this thing that Google Street? What's this? street view. So you see also sometimes it's blurred, right? Well, what do you have there? Well, you have noise there. You know, you can say, well, because we took many cameras put together, but you have noise. So what would be the right thing is maybe denoise it. So one of things, denoise it, it means you should filter out the lower frequencies, which are this one. If you do that, you may improve. It's not always true, but so you can do that. Okay. So this noise reduction applies in image processing, DNA microarray, and data compression. Now how about data compression? Why it's important in data compression? Okay, so in that is essentially a problem in a very big data that. Okay, so let's see. So what you do, you have many, so you take vectors which is sort of rows and columns. So in other words, you have several rows and columns of the same pictures, not exactly, and then you just take several of them. Instead of, let's say, 1,000, you take only 100, or if you're lucky, maybe 10. So suppose it was only 10. So you have to take a storage only of 2 times 20 vectors, which is much less. So that's how you do a storage. Okay. So now, yes, questions? Okay. So now the next thing is the next thing is what one can do is, well, and that is a problem actually. Even somebody contacted me. He had a big DNA data, and maybe he didn't have a supercomputer. So how do you, if you have a very big data, how do you process it? Usually you cannot process it, let's say, online, because it's millions by millions. So what is the solution? So that is essentially what is this part of this talk. I'm not going to all technicalities. Essentially is how would you try to reconstruct your data from taking, but you assume that your data is at least 2-dimensional by taking some number of rows and columns and try to reconstruct it together. Now, in mathematics and also well in applications, you don't know let's say which rows that you pick up and which columns that you pick up would really contain most information. So therefore, the best solution is take it at random. In other words, you have something, suppose you have 1 million, okay? So it's sort of like going to Las Vegas and say, or lottery, right? So you just say, well, I mean, I just call my computer to pick up, let's say, 100 numbers at random. Okay, so that is random process. So in this way, you mean that you don't have any information, and the information is spread is sort of at random. And if you pick up enough at random, but not too many, you will have most of the information. So this is in many algorithms. That's how it works. So here, sort of in this let's say topics, I suggest how to do that. But I don't think that there is any point to go to the exact algorithm unless you will ask me to give the details. Now, what one can look here also, so sort of, okay, so here is, so what we do usually, we do something like simulations. Now, again, this is terrible. I cannot see anything. I hope you can see something. Well, okay, so what we see, we see this lifting body image. Now, so it's always in mathematics and engineering the question is of price. You want to do something better, it costs you more money, and in computation means it costs you more time. So the idea is then you say, can you produce something efficiently, fast enough, and cheap? So in this case, cheap means less computation. So if you want, given your data and you say 2-dimensional, I want exact SVD and then it costs you much more. And if you take the, let's say, an approach that you pick up at random certain number and do some computation, so this is sort of, this graph shows you that after a few, so this would be on the bottom, would be sort of the best that you can achieve by using rigorous computation. Here you see that after maybe 4 or 5, you already are at the best. But essentially, if you look at the scale, I mean, this is 10 to the power minus 4, so it's good enough. So this is simulation number 2. So this is for cameraman.
What are the axes on the graphs?
Okay, let's see.
Picture's kind of small and I can't really.
Okay. Well, we can do it very. Okay. So let me take back and just increase the. Yeah. So let's try to increase it. Okay. First of all, let's take one picture, and let's try to increase. Can we do that? Okay. So now, can we see now?
Yes.
Right.
So
Okay.
The error there is measured at the Frobenius norm.
Okay. So. Okay, so right, so let's see. So here, let's see. So right, the error here, I think it's in the Frobenius norm. So I want to approximate rank 80, let's say, for example, right? So you say, so this is this would be the best, I think. And here, if you do this, maybe let's see. If I remember that, let's see. It's. Okay, let's see. So first of all, the error, I would think it's a relative error. So you take A. Okay, let's go back and let's try to explain. So what is the error here? Okay, right. So let's see now. So let me just take it slightly smaller, if I can do that, just to see. Okay, so here, so let's look here. So here is, I think that if you get up to 0 or something, that will give you that you restore the full matrix. Otherwise, you take A minus AK, so the difference in the Frobenius norm, divided by A. So it's always a relative error. Now here, you say, well, if I want rank 80, my original matrix won't rank, so this would be the best I can do. Now here it tells you that here is that what you do with the random, but you don't have the full sort of SVD decomposition, so you get to a certain limit, as far as I remember. Okay. Now, so what else we can do here? Let's see. Okay, so maybe slightly go back to a smaller scale, and then. Okay, let's see. So. So again, so here this graph just tells you that it's that you have sort of the price that you pay maybe 6%. You have error in 6%, but you have a speed up of 3 times. Okay, okay, so what is the next thing? So the next thing is, so now, so let's go to the sort of bigger picture. So the next topic we can do is, let me just try to make it smaller, is how to reconstruct, to give you the idea how to reconstruct, let's say, some missing data. So again, so you suppose let's say, you send something to Mars or farther away, it sends you back the pictures and there are some spots. You cannot do it again, or it's too expensive, or you do some microarray experiment, and because it's very big, you always have some spots. So first of all, you have to decide that those are spots that are missing, and you want to reconstruct so you want to reconstruct this spot. So how are you going to do it? Well, again, there are several ways to do it. Okay, so let's see. I'm not sure. Let's go. Okay, so let me just try. Okay, so here, so what is the idea here? So this, we are discussing now this missing entry problem. So you have, can you read here? Okay, so you have some data and you're missing. So how we reconstruct it? So what is the idea? The idea is as follows. Just explain it. So I assume that in my data, let's say it was 512 by 512, say, but the rank was only 20 or only 5, rank 5. So that's a sort of, I know from other pictures or from other experiments that effectively the right rank is 5. So the idea is here that I complete the data in such a way that I am close as possible to rank 5. And if you do that, you can come up with the algorithm which works. Now, so this is the algorithm. So I'm not going to discuss, anymore. I mean, I don't think it's. So you would like to know all these details, but let's see just again. So when you do like that, do simulation. So you compare several methods, and you can say, well, in every paper that you see, they say, well, my method is the best. So it's always, you can always cook up a data. Well, we didn't try that. Your method is the best. So in this case, you see that our method is sort of compares favorably with other methods. Okay, so what else? Now the other, okay, so what else can you do with this singular value decomposition? So the other topics that let me just show you what you can do is to compare. So as I said, you have suppose, let me just see. I probably should do something faster than this one. Okay, well, anyway, I don't know how to do it. Okay, so the idea is, suppose you want to compare the microarray of human to a microarray of yeast. So you want to see sort of what is the common features and what are different features. So how would you do that? So for that, if you want to compare two sort of pictures and say, well, or two microarrays, you see, how would I do comparison? So I see that some functions are similar and some functions are different. So for that, okay, this is terrible again, but we have this tool which is called Generalized SVD. Again, this is tool, it's not found by me. And actually, it was successfully applied by Orly Alter, that she got her, I think, PhD in experimental physics in Stanford, and then she switched to DNA and, let's say, bioinformatics. So it is sort of the same tool, but SVD, but now you do SVD with two matrices. Now, just to explain briefly, because I don't think that now you, instead of taking matrices which are sort of orthogonal, you cook up a new metric. You sort of change change the distance when you measure, and then you have a common decomposition of these two matrices, and from that you can see what is common and what is not. Now, what can you do with that more? I really don't know, but that is this method. So, okay, so what else? Let's see. So, okay, so now the final thing is about tensors. So let me just give it briefly. So, okay, so let's see here. Okay, so I should take it smaller. So what is the problem with tensors? So tensors, so in this particular talk, we are talking about 3 tensors. So suppose you measure a 3-dimensional picture. Now, you see, when in mathematics we have real numbers and complex numbers. I'm not sure if anybody of you used ever complex numbers, but they are sometimes they are good to have in physics or in electromagnetics. Now, the theory of, let's say, SVD or 2-dimensional picture, it's all real. You start with reals and you approximate with real, everything the same. The problem with 3-dimensional tensors, if you start with real, but you want to condense as much information, it's better to do it when you go to complex numbers. And this already right away tells you what is the problem. Now, so essentially there is no SVD for 3 tensors. You can do it if you want to do it, really condense it, then you should do it, you should go over complexes. So the standard thing now, it's done, let's say, for this tensor, is called flattening. If you have 3-dimensional pictures, you say, okay, you know what, I'm going to okay, how should I say? So if 3-dimensional pictures, you can take pages, okay? So you say, so therefore, so I'm looking only a page, number of pages, so it's page number 20. Now I look at the text here, then I say, okay, this text is going to be just 1 line. So what you did, you took a tensor, you took 3-dimensional picture and flattened it into a 2-dimensional, and then say, aha, now I know how to do SVD. But of course, by that, you lost the 3-dimensional picture. So then it's useful what to do is to go, let's say I have 3 variables, 3 dimensions, to flatten in each different direction to do this SVD and try to combine them together. So it's not optimal, but essentially that's what it's done in practice. And in this conference last year in Stanford, Yahoo Stanford, they were discussing this approach in, let's say, in face recognition, because if you want to recognize a face, that's the technique that's available right now. Well, I think that I presented. Okay, so I presented most of the problems in this talk, and I think this probably is the right time to stop and let you ask questions. Yes?
So in doing these approximations, do you usually assume that the individual values have unbounded precision or are limited to some number of bits of precision, like the original?
Okay, so let's talk about SVD. Okay. Well, you have to assume that it's fine, that you have, if you want to be precise, take double precision. That's it. I mean, that's all the computations are done usually in double precision. So it's not, so you have to compromise. It's just a mathematical thing. Yes? Other questions? Yes?
So this method, like when we use 3 dimensions,
them, right?
Can we generalize this to 4 dimensions?
Oh, yeah, sure. It's no problem. It's no problem. Just say, okay, but then you have, you just say, okay, so I have 4 dimensions, so I took 2 dimensions and squeeze it to 1. So So let's see if I'm not sure. So tensor is, let's say, 4-dimensional tensor is I, J, K, L. So I and J runs from 1 to 10. So let's make it, let's say, IJ as just index, and it would be IJ 1 to 10 would be you have 100. So yeah, and again, so yeah, so it's this technique is universal.
But then, like, if we have large number of dimensions, it will explode. Like, it will have lots.
Well, yes, but anyway, so anyway you put, tensor is, suppose you have 10 by 10 by 10, so it's 4 times it's 10 to the power 4. So the number of data, this is that's to do with the tensor. The question is how to approximate is good with trying to reduce the dimension of a tensor as a rank. But so you can do it, you can try to do it, but if you have big data, there is no way. That's the big data. What you're trying to do is sort of to decompose it in such a way that you have to store it much less and preserve most of it. So you can, yeah, you can, if you have 4 dimensions, you have more freedom, but it's the same idea. Other questions?
All right, well, thank you very much for coming.
Thank you.